All right, so we are in time. We're very happy to have Steve Callander from Stanford PhD talking about efficiency solving complex environments. As Chance suggested, some of the techniques in Steve's work have inspired a lot of the way people are modeling experimentation in economics, and we will see other versions of this in the further.
Thanks, Laura. Morning, everyone. It's great to be here. It's been a great start to the conference. I'm going to hope I can keep it going here. So I'm going to talk about some of my work in this area, in particular around strategic communication. And I'm going to, what have I done? It's going. There we go. I'm going to focus on a current working paper. Oh, well, it's not actually a working paper yet for distribution, but it's almost. It's work in progress with a PhD student from Stanford, Eunice Abas. Use that one. Good to have the right clicker. All right, great. So, given this is an interdisciplinary conference of economists, computer science, and related fields, to put into context what I've done, what I've been doing with my work, I thought it'd help to just start by sort of characterizing how economics approaches modeling decision-making under uncertainty. The sort of classic predominant approach in economics is best put as to simplify, simplify, simplify. All right, there's a complex world, there's a lot of variables, a lot of decisions, a lot of stuff going on. What we do in economics is we simplify it, simplify it, simplify it, and then we tell you exactly what's happening in that simple environment. All right, we give you optimal solutions. There's none of this sort of algorithms approaching optimal solutions. We give you the optimal solutions and we'll tell you exactly what happens. All right, and that's great. And I'm an economist. I'm a fan of this approach, but that's what we do. And the point being, though, that of course we're throwing out a lot of information throwing out a lot of important things then when we model it that way. All right, and so when we think about decision making under uncertainty in a variety of domains, there's no simpler way of modeling uncertainty. There's no more reduction you can do to then reduce it down to a single piece of information, a single unknown. And this is essentially, it comes up in many domains, but in particular in the classic one-arm bandit model. All right, you've got a safe option, you've got a risky arm, you just don't know if the risky arm is good or not. Make it an interesting problem. We say, well, it's difficult to learn whether it's a good arm or not. And then the question, the research question becomes, when do I stop pulling that arm? If I want to experiment, I know what arm to pull, I'm going to pull it, and I have to decide when do I stop pulling that arm. Right, but in particular, there's no choice or strategy around which arm you pull, how you're learning across those arms, and so on. Right, now, I should say this has been extended. There's multi-arm bandits. We even go up to denumerable arm bandits. So there's a lot of bandits, but when they're independent, right, the problem still basically recurs of when do I stop pulling that arm. But when we think about practice and uncertainty and experimentation in practice, there is a lot about the world that we don't know. All right, it's more than one single piece of information. And that information that we don't know is correlated. I don't have to go into too much depth right now, since we've had two nice papers already this morning, talk to you about correlated information and learning correlated information. But once we start having multiple experiments to run and those experiments are correlated, we get more, I think, interesting questions like, which experiment should I run? What am I learning from one experiment to the other? And it's not just, whether to pull the arm and how long to pull the arm for. Right, so John and Yari's paper is great. They use the Brownian motion, this continuum of correlated random variables, and they focus on continuous search. Right? And they get the question of not only when do you start, when do you stop, but what the speed is that you're going to experiment to learn across these arms. In some of my work I've done on experimentation, I focus on discrete time, and I allow the experimenters to choose any action in the real line they want at any time. Right? Now, if you're thinking, wow, that's a big generalization of what John did, well, I usually do myopic search when they can do this, and he's big part of his contribution is being able to do it with forward-looking agents who can solve that problem. And so what we're interested in is not just sort of whether you're experimenting or not, but what action you're choosing, what experiment you're undertaking, and how you learn across those different choices. All right, I really think it's important to drive home how important this correlation is to to learning in practice. So I want to just give you one example that I've found very useful to think about, and that's about young people, perhaps like yourselves, who are going out and getting jobs. All right, so when you finish college, or maybe when you finish grad school, you're going to go out and get a job in the real world. Not that grad school is not a real job. I mean, we all know it's a real job. But suppose you go outside of academia and get a job. And suppose you decide you want to go into finance and you take a job at Goldman Sachs. All right, now that choice itself to go into finance was deliberate. That was directed. But suppose you work at Goldman Sachs and you learn that you hate it. You work 100 hours a week, your boss is mean to you and he yells at you constantly. All right, what do? You quit. But what do you learn from that experience? What job do you take next? You go down the street to Morgan Stanley and say, oh, well, I'll try Morgan Stanley. Like I pulled this one out of the hat, it didn't work. Let me go next door and pull the next one out of the hat, at Morgan Stanley. All right, what's going to happen? Those jobs are going to be almost identical. And so if you hated having a boss yell at you and work 100 hours a week, you're going to hate it at Morgan Stanley as well. So what are you going to do? You're going to do something very different. Maybe you did this before grad school and that's why you're in grad school. All right. I did that. I worked in finance for a year. It wasn't a pleasant experience. I got as far away from that as I possibly could. And I went and did a PhD. Right. The point is you learn you not only don't like Goldman Sachs, but you're learning about the other alternatives. And there are other alternatives that are close by, like working at Morgan Stanley. And there are options that are further away, like going to grad school, becoming a teacher, becoming a farmer. All right. So the point is when we're experimenting about almost anything, we're learning across alternatives in this way. So this correlation is super important. And that's what we're trying to model when we write down these models where there's a lot of things we don't know and there's correlation across them. So very good. And then John's nice result about it's not satisfying. All right. His idea is you get a good draw, you get the Goldman Sachs. Suppose you went to Goldman Sachs and you loved it at Goldman Sachs. What do? Right, in the classic independent bandit model, you would just sit there and say, I'm above my satisfying level, I'll stop. Right? But I think the more natural thing is to then look around in finance for an even better job. Right? If you like your boss yelling at you, go to a hedge fund, they'll yell at you even more. All right, you go for 120 hours a week in an even more extreme boss. Right, that's what you do. If you like Goldman Sachs, you think, hey, maybe there are other good jobs around here that are even better. Let me search a bit. You go to a hedge fund, that's terrible. So what do you? Well, it's not terrible. You don't like it as much. You go back to Goldman Sachs. All right. So once you've searched a bit around and you realize, no, Goldman Sachs was the peak, you go back there and you stay there. Right? You don't get that with independent bandits, and so that's what we get with correlation, and that's a really nice feature of that result. Right. I should mention Annie's nice paper before it, which also added the question of how you allocate in a different sort of related but different structure, how you allocate your attention or your research effort across these different correlated sources of information. Right? That's another, as I understood, another dimension to expand upon these classic questions of just whether you're experimenting or not. Right? But how do you allocate your attention as you experiment? Right. So what I'm going to do, I'm going to stay in the same line of work as John's paper that uses the Brownian motion. All right. But what I'm going to do is focus on a cheap talk model or a communication model using this structure. All right. Very good. All right. So another problem we have in economics, we study a lot, is that of strategic communication. There's an expert who knows something more than the decision maker, and the decision maker has to make a decision. And so the question is, can that expert use her information to influence the receiver's decision? Key to this is going to be that their preferences aren't exactly aligned. This was, I think, the fourth category on Theodorus's summary at the start, the strategic interaction, the adversarial relationship between players. All right, so we're going to have an environment where there's a decision maker who makes a decision, an expert who has better information, and the question is whether she can use that information to influence that decision or not. All right, so to just give you a little bit of formality, the classic way of doing this, the classic economics way of simplifying is to say, the expert knows one piece of information the non-expert doesn't. That's going to be this real valued variable. It's usually omega. I'm going to call it beta. And it's just going to be in between 0 and 1. Then the game is pretty simple. The expert sends a message to the decision maker who doesn't know theta, and the decision maker has this bias. And I'll talk about that a little bit more, but basically her preferences are different. The outcome he is trying to achieve is different from what the sender wants to achieve. And this B parameterizes that bias. This very simple game and this very simple informational structure is the basis of two classic literatures in economics. One is the cheap talk model of Crawford-Sobel 40 years ago this year. And in the cheap talk model, the message is cheap talk. The sender can say anything. She's not constrained by her information. So in other words, she can lie. Right? She can tell you whatever she wants. And then the question is, can that cheap talk influence the decision maker's action? The second literature from around pretty much the same time is about verifiable or hard information, where the expert can't lie. She doesn't have to tell you the whole truth, but she has to tell you something that's not untrue. All right, so for example, if theta is equal to a half, she could say theta is somewhere between 1/4 and 3/4. Now that's not a lie, but it's not telling you everything. Right, that's the verifiable information case. The idea is you could go to court and a judge could just tell you whether she was lying or not. Right, so these are two classic literatures. Today I'm going to talk. I've worked on both with this Brownian information structure, but today I'm going to talk about the cheap talk world. Right. So that's the classic model. Now I've already made this point in terms of experimentation that the real world is more complex. There's more things we don't know than just one piece of information. I think the same applies to experts. Right? If you think about any expert in practice, they know a lot more than a layperson does. Right? For example, you go to a doctor. It's not like you go to a doctor to get medical care and the doctor has this one single dimensional variable of information that she knows that you don't know. Right? I hope they know a lot more than we do. Right? You can think of a mechanic. You go to your car mechanic. Why do people have a queasy feeling when they go to a mechanic and get their car fixed? Because you think the car mechanic is telling you BS and ripping you off. Right? They know a lot more about fixing cars and what's wrong with your car than at least I do. Another big application in economics is the boss and the manager, the owner and the manager in firms and within organizations, within political institutions and so on. All right, and I put this up here to just say, we're all in this bucket as well, at least the economists here. We think we know more than one single piece of information than the rest of the world. All right, so we hope we fall into this grouping. All right, so what I'm going to do is I'm going to try to expand upon this very classic simple model in the cheap talk setting, and I'm going to try to enrich the model of expertise to capture some of this richness. And how am I going to do it? Well, as you saw in the last talk, I'm going to use the Brownian motion to represent reality. So now the state space isn't this, the state space is going to be the realized path of a Brownian motion. The whole path is there, it's fixed at the beginning of the game. And the idea is the expert knows that. The expert knows a continuum of random variables. I've gone from one to a continuum. These random variables are correlated. The expert knows these random variables and the non-expert doesn't. And so the question is, how does this affect communication between the expert and the non-expert? And how does it affect the expert's power in that communication? And what I'm going to try to show you is that this expansion of the state space to a Brownian path, right, substantively changes the nature of communication, and it changes sort of the logic of expert power. It provides, I'm going to try to argue, a foundation for expert power in this cheap talk setting. All right, great. All right, so many of you don't know the cheap talk literature or strategic communication. So let me just tell you two classic intuitions that come out of the canonical models, the Crawford-Sobel model, and much of this work after that. All right, so if you read Crawford-Sobel, you read the cheap talk literature, two sort of prominent conclusions come out of it. One is the communication, even though it's cheap talk, even though the sender, the expert can lie, communication can be valuable. But as long as their preferences aren't aligned, as long as there's some bias in the receiver's and the decision maker's preferences, communication is going to be inefficient. All right, we're going to lose some information. It's not going to be as good as we could get. It's just not going to be efficient. And the other striking prediction that comes feature that comes out of these models is that the expert herself has no leverage, has no power. The expected outcome in the canonical Crawford-Sobel model is with noise because it's inefficient, but it's noise around the receiver, around the decision maker's ideal outcome. So the expert has no leverage. Right? In fact, this implies that if the expert could give the receiver, give the decision maker her expertise at the start of the game, she would, and they'd both be better off. So to me, that's always struck me as a bit of a weird prediction about experts and expert power. When I think of doctors and mechanics, managers and economists, I think you have some power because you're an expert. Right? You have some leverage, some ability to influence the decisions in your favor. But we don't get that out of the canonical model. And what I'm going to try to show you is that when we enrich the state space to be the Brownian motion, I'm going to restore that prediction. I'm going to find that communication can be efficient and it can restore the expert's power. All right. So that's the preview of results. You know what I'm doing now. I'm going to study this classic game. I'm going to generalize the state space, make the expert know many things rather than one thing. And what I'm going to find is there exists an efficient cheap torque equilibrium, so we don't waste any information. The equilibrium I'm going to identify as expert optimal. And in fact, the expert is going to get her ideal action in for every state. And so consequently, the outcome I'm going to get is not only giving the expert some power, but it's as if the decision maker has delegated the decision to the expert. She doesn't have just some power, she has the power to get whatever she wants. Right now I have a quote from Max Weber, the famous sociologist who's written a lot about power and experts, in particular in political institutions. So this is just a quote to say this result, I think accords better with how we understand experts in practice. As I said, you go to a doctor, you don't go there thinking, you have all the power when you're talking to a doctor or a mechanic. Their expertise allows them to influence decisions in their favor. That's what we understand about expertise. That's what Weber understood about it. My point is this richer state space is going to give us that. All right, very good. So let me.
Sorry, Steve.
Yes.
Sorry. Is there an? I thought there was an old literature in cheap talk which was multidimensional, and they already sustained
with multiple senders.
No, with multiple dimensions on the state, where you can get full revelation. If you're not aware, we can talk about it afterwards if that's not.
Which paper are you talking about?
I think it was Battaglini.
It's in multiple senders.
Oh, it's multiple. Sorry, I'm wrong. Okay, so there are no where the state is.
Yeah.
Multi-dimensional.
Yeah, they're very nice papers, but yeah, multiple senders.
Got it. Cool.
Yeah. We'll talk about it.
Sure. No.
Yeah. All right. All right, so here's the model. I'm not going to get into too much formality. So if I'm going to try to put it in words and then some notation, if anyone gets, I often get this balance wrong. If I miss notation or something's confusing, let me know. I'm happy to clarify. All right, so we're going to study the canonical cheap talk game of Crawford-Sobel. We're going to stay as close to that as possible. And in fact, we're going to focus on what's come to be known as the canonical classic example, which is the expert has constant bias B and everybody has quadratic loss utility. Right? We don't need these things, but it just makes everything a lot cleaner and the intuition a lot sharper. Right? So in particular, maybe let me do this point first. What's going to happen is the expert's going to learn the state, the Brownian path, send a message to the receiver. The receiver is going to choose an action, which we're going to put in an interval, and this is going to be important, 0Q. Right? And this action is going to map into an outcome, and that's what they care about. Right? So they can control their action, they care about outcomes. The expert's ideal, the decision maker's ideal outcome is 0. He wants an outcome as close to a 0 as possible. And this is the bias. The sender, the expert, wants to get near outcome B. Right? If B was 0, their interests would be aligned and there'd be no tension here. You could just share your information and everyone would be happy. So this is the bias that's creating this tension. All right, so what's the expertise? So as I said, I'm going to model it as the realized path of a Brownian motion. Drift mu, variance sigma square, these things are known. Everybody knows how the world is generated. They know it's generated as a Brownian path. The expert knows the whole path, the whole realization, the non-expert, the decision maker, knows the drift, the variance, and we're just going to assume he knows a starting point, a status quo point. So the outcome of action 0. All right, we can relax that too, but it makes it cleaner to do this. It just makes it easier to see. So this is a Brownian path. You all know what these look like, very complicated, jagged sort of functions. Right. We can contrast that to what the canonical model, the Crawford-Sobel model is. So their model in this setting is equivalent to a mapping that is the state of the world minus the action. So their model is equivalent, and I'm going to give you a picture in a minute, to the expert knowing the intercept of a linear function of slope -1 in this case, and the non-expert not knowing it. So we fit exactly in their world. All we're doing is, instead of using this function, we're going to use the Brownian path. So let me give you a picture. So here's the model in pictures. I'm a big fan of pictures, so I like to do everything in pictures. This is my environment. This is the classic environment. Right, so in the classic Crawford-Sobel environment, we know the true mapping is a straight line of slope 1. We just don't know the intercept. We don't know this theta. So we don't know if it's up here, if we don't know if it's down there. All right, if the state is between 0, 1, we know it's in some band or whatever the state is in, but we don't know which straight line we're on. Here, the players know some starting point, but then the true path is a Brownian function. Right? And what I have drawn here is the red dashed line. That's the drift. I'm going to have non-zero drift. In this case, negative drift. All right. So the non-expert knows, given this outcome, if he chooses an action further to the right, the expected outcome is following this drift line. And so if he wants to get to outcome 0, he's going to move to the right and he's going to get a better outcome in expectation. But the variance is increasing as the action moves away from this status quo known point. So this is going to be the essence of the decision maker's model. He knows one point, he knows where to go, which action to choose to move the outcome towards his ideal point, but in expectation. And the further he moves from the point that's known, the more variance there is. So very good. So they're the two, my model contrasted to the canonical model. Right? And this picture allows us to see pretty simply what happens in the canonical model and why my model is going to be different. All right. So suppose the expert was to reveal an action. For some reason, I'm going to call it M star. Like she says, do M star. She says, do M star. And so suppose in equilibrium or whatever, we know that's going to produce outcome B. You can do that with my Brownian motion as well. Suppose it happens. Right. Now, what happens in the canonical model? Well, now in the canonical model, instead of I had uncertainty over which line I'm on. Once I know one point in the mapping, and it's a line of slope -1, I know exactly what mapping I'm on. And so this is the key phrase. The expertise in the classic model is invertible. As soon as I tell you one thing about that mapping, you know the whole mapping. All right, if that seems weird to you, it seems weird to me, and that's why I'm working on these models. Right, so in other words, this is a doctor telling you, here's some treatment you should have. It's good for you, but it's more care than you may want. Right, that's my bias. The doctor always wants more care than the patient wants. Right, but from that, you can invert the doctor's expertise such that you know exactly what line you're on. And in particular, you can then say, thanks for that recommendation. I'm going to do A star because that gives me my ideal outcome. And so this is the core problem in Crawford-Sobel. Because the expert doesn't know much, it's very difficult for her to use her information in a recommendation, but also keep it private at the same time. Right? Because if you give it all to the decision maker gets what he wants. So to sort of one way of putting it is to have influence as an expert, you've got to share some information, but not all of it. And so the point is, if I share all of the information about one action, you have all of it and I have no leverage. And so the beauty of the Crawford-Sobel results, I mean, this is a fantastic result, is to say, given that invertibility, can we still communicate strategically? And the answer is perhaps surprisingly yes. All right, and what they show is you have to, you have to chop up the action space in equilibrium. So instead of having all actions on the equilibrium path, we reduce it to 2, 3, 4, or some finite number, and we cluster our messages, and we can still get efficient communication as long as the bias is not too big. Right? And that's a beautiful result. But when we do that, we're communicating inefficiently, right? Because we're adding noise to our message. So that's the inefficiency in the classic Crawford-Sobel result. All right. So what happens in my model? Well, now I tell you a point. Yes, so this is just conjecturing. Suppose I tell you message M, and you know, you're the decision maker. You know this produces outcome B. Right? You want outcome 0, but you know a point that's B. Because this is a Brownian path, you learn something about this path. You know it passes through this point, and that changes your beliefs, but it doesn't teach you everything about the path. Expertise is now partially invertible. I'm teaching you something. I'm teaching you one absolute point. That changes your beliefs about all of these values because now you have a bridge between those 2 points. Now the drift line is my green line that comes from that point. But I'm not telling you everything. So I'm using my information to give to you, but I'm not giving you everything. I think that's a pretty basic sort of intuition, and it's one that the Brownian motion representation really conveys very nicely, I think. All right, so very good. All right, so now I'm going to say, well, you know, what happens here? Can I support equilibria and what's going on? All right. So let's take this model. Before I can tell you the equilibrium result, I need to tell you what does the decision maker do without an expert? And that's just because that's the background action in this model. You're wanting me to communicate with you, but if I don't give you the information, you have to make a decision on your own. All right. And so this is sort of the background context to expert advice. So this slide is a little busy, but what I want to convey is, so suppose there's no expert. We talked before about, if this is the known point, as you move to the right, you're getting a better outcome in expectation, but you're adding noise, adding variance. All right, so you trade classic economics, you're trading off risk and return. Because I'm going to assume quadratic utility, this trade-off comes out super cleanly, which is, if you start at some point here, you choose the action that has expected outcome alpha, where alpha is the ratio of the variance over the drift times a half. Right, so this ratio comes up a lot in this paper and my other papers. All right, so basically, the risk is worth the extra return until you hit this level, and then it's not. So that's what you choose. So if the status quo point is beyond alpha, your optimal experiment on your own is some I call it A to the n0, no expert, that has expected outcome alpha. If the status quo outcome starts lower than alpha, then your optimal action is to do nothing and just keep the status quo. Well, I shouldn't say do nothing, is to just choose the status quo, to not experiment, to not undertake any risk. So basically this alpha is the key threshold with quadratic utility in this world. It's where the risk return trade-off transitions. All right. So if there's no expert, the decision maker chooses an A and 0, where if the status quo is beyond alpha, he chooses the action that gives expected outcome of alpha. And if it's less than or equal to alpha, he just stays at the status quo. So that's the risk return trade-off.
Question on the picture. So I don't know. The starting points of the two Brownians are different here. So I thought you were pinning it at one end.
So this is just two different examples. So this is, suppose it started here, and this is saying, well, suppose it started here. And I'm going to parameterize the starting point.
Question about the problem setting. So decision maker knows the mean and variance and don't know the path, right? And an expert knows everything. And in this picture, still the decision maker don't know the path.
Yeah, so the decision maker also knows the starting point.
Yeah.
But it doesn't, yeah, so it doesn't know the path. So I should probably get rid of the path and just say, you know, your decision problem is choose an action that has expected outcome on this line and with variance increase. As well. So that's what you do, the decision maker does without an expert. Right, so now let me tell you what happens when there is an expert and can we have expert advice? All right, and so now I'm just going to deal with this case where the status quo point is beyond alpha. And I'm going to study a strategy that we call a first point strategy. So the sender uses a first point strategy means she recommends the first action that gives her her best outcome. So she looks at the whole path, she finds the actions that are the best for her, and she recommends the first one. And by the first one, I mean the one closest to zero. So when the path is the whole real line, that is almost surely outcome B. This is a Brownian motion with negative drift. It's going to cross B at some point with probability 1. So now the question about equilibrium is, if that's the recommendation, will the receiver, will the decision maker accept that recommendation? So very good. So this is a depiction. The receiver, the decision maker knew the red line. The experts now come along and said, here's my message, where my message is the recommendation. You should do this action. It's cheap talk. There's no verifiability, but in equilibrium, the decision maker infers that this is producing outcome B. Now he's learned something more about the mapping. He now knows 2 points. Question is, does he accept this recommendation? And for small bias, less than alpha, that's what he's going to do. All right. So why is that the optimal thing? Well, he knows that he doesn't want to choose any actions to the left because the 2 things he's learned about the mapping are, well, he's learned 3 things. 1, it starts here. 2, it passes through this point. And the 3rd thing he knows is this is the first point that this path crosses B. Because remember, my strategy is the first point that gives the optimum. All right. So her beliefs between these 2 values is not a bridge. It's not a classic bridge. It's a distorted up bridge because he knows it does cross B. All right. I don't even need to tell you what that distribution is because clearly this is better than any of those actions. All right. So now the interesting thing is, why does he not move somewhere to the right? Right. And I hope what you're realizing is, well, that's why I had B less than alpha. Right? Because if B is less than alpha, I go back to my non-expert decision making without an expert. And I knew that if the point I knew was less than alpha, the risk return trade-off isn't worth it. And I just stay where I am. And so this first point strategy is in equilibrium for small bias. The expert recommends an action that maps into outcome B, her ideal point, and the receiver implements it. So we get 2 properties from that. 1, it's efficient. We're not wasting any information here. All right. I should probably be careful about my efficient definition, but there's no noise in the messages. Right. And 2, the expert has leverage. The expert is now getting an outcome closer to her ideal point than the receiver's optimal. Very good. Great. All right. So that result, I actually have in a paper from over a decade ago, and it's taken me that long to figure out what to say next about larger bias. All right. So that's what the paper in progress is going to tell you. Very good. All right. I think this is just a picture of, this is just a picture of what I was talking about. All right, I've already said that. So let's go to larger bias. And in fact, what I mean is intermediate bias. Let the bias be somewhere between alpha and the status quo outcome. All right, I'll tell you about beyond the status quo outcome later, but this is what I want to think about now. All right. What happens now when the action space and the message space is the whole positive real line? All right, well, now we're going to have a problem because now under the same logic, the sender sends a recommendation. I know it's going to be this point, but now B is above alpha. And so that's great. The receiver, the decision maker says, fantastic. I now know a second point, but that tells me I actually want to do some other action that will produce outcome alpha in expectation. Is that my next picture? Yes. All right, so the expert shares some of her information. The receiver, the decision maker uses it, but choose something else. All right. So my first point strategy falls apart as an equilibrium in this case. And now you might say, well, this could still be optimal, but of course it's cheap talk. So if the decision maker knows the receiver is going to move this far to the right from the recommendation, now what she does is she recommends something over here, anticipating that, and it all unravels. All right. I don't know what the equilibrium, anyway, let me come back to it. Very good. All right. So how do we support equilibria? Well, I don't want to call it a trick, but what we noticed was if the action space is bounded, right, I can support this first point strategy as an equilibrium. So the fact that the action space was the entire positive real line, all right, was important. So let me bound it to some interval 0q. Does this matter? My answer is going to be yes. And the reason why it's going to matter is if I bound the action space, there is now positive probability that the Brownian path doesn't actually hit B. When it was the whole real line, I emphasized with probability 1 it hits B. If I've got a bounded interval, that's no longer true. And this is going to be enough for me to support efficient cheap torque equilibria. All right, so what happens when I bound B? I got to like 5 past. Is it?
Yes.
All right. Very good. So what happens now? Well, now if the expert recommends action M star, right, there's 2 possible events that are happening. Right? The first one is, and the receiver, the decision maker doesn't know which one he is in. One possibility is that the path does hit B, all right, and that if she follows that outcome recommendation M star, it's going to get outcome B. The other possibility is the mapping looks something like this, where it doesn't actually get to B. We're going to call this event A and event B. And so now, because the decision maker doesn't know which event he is in, right, this is going to affect his incentives to accept the recommendation. Why? Because if we're in this event, he doesn't want to follow the recommendation because I'm thinking of B above alpha, he would move to the right. But in this event, he does want to follow the recommendation because this is the best outcome for the expert. It's above B. That's also his best outcome. And basically what we have to do is a lot of work to prove that in some circumstances, this event is going to dominate the first event. And so it's going to be optimal for the receiver, for the decision maker to follow the recommendation. Right? I'm not going to get into any of the formula, but we have to do 2 things. We have to characterize the beliefs of the decision maker given these 2 events. All right. And in event A, it's the first hitting time of a Brownian motion. What's the probability that the first hitting time of the Brownian motion at B is M star? And in the second event, it's what's the probability that the minimum of the Brownian motion is at M star? And also it's the last minimum in the sense that the path must go up afterwards. All right, so we've got a bunch of densities of our hitting probabilities and various things. We've got to put them all together, all right, and be able to compare the probability of event A and B. What we also have to do is say, given those beliefs, it's not optimal for the decision maker to deviate. Right? And in fact, just this week, we were able to characterize exactly the distribution of outcomes given these 2 events. And so we can characterize exactly the expected utility of the receiver, of the decision maker in equilibrium.
It feels like you're saying this is universal. It doesn't depend on what sigma or mu is.
It absolutely is going to depend upon us.
So
I'll give you, we're going to do it in terms of Q, the size of the interval, but it absolutely is.
there is some interval as a function of sigma and mu.
Yes.
So is it fair to say then that like shrinking the size of the interval is like the equivalent of reducing the bias in corporate circle? because it's like reducing the probability, it's increasing the probability that you might actually just be aligned, right? Is that or am I up the wrong tree?
Well, probably say, well, if you change the bias, you're either aligned or you're never aligned. So
fine. So
the way I put it is that Crawford-Sobol interests are opposed, and they show how you can get aligned interests by partitioning the message space. Right? I think it's pretty simple, but what we're showing is how the possibility of aligned interest can come from the environment as well. You know, and so this is a natural, I think, way of showing where that alignment comes from.
I totally agree.
Yeah.
I just think that like
so the whole, yeah, you're right. The whole literature is about cheap talk just doesn't work if there isn't some alignment of interest. And they get it by partitioning the message space, and that's what's surprising and beautiful about it. In some ways, we're going very simply. We're just saying the environment can naturally generate this alignment. And so I'm going to run out of time, but my main result is going to be for all bias up until sigma 0, the status psi 0, the status quo point, there exists a cube upper bar such that a first point equilibrium exists. Right? And in fact, it's going to exist for all q less than that. So if this bias is less than alpha, q upper bar can be infinite. It can be the whole real line. But once it goes beyond alpha, I've got to stop the interval at some point, and it's actually contracting as the bias is getting bigger and bigger. All right, and so I could parameterize alpha and sigma squared instead. I'm just doing it through the size of the action space. Yes.
It's another interpretation that you're making some talking verifiable or giving the instance now with math such that it's always below. I will tell you Q, right? Or like there is one message that now I can convey.
So, well, there's no verifiable information. The Q, I'm thinking of as an exogenous parameter of the model. We're going to get into that with delegation, but I won't have time to get into it today. But yeah, it's just a feature of the model. It's a parameter of the model. And I'm not quite sure where you're coming from, but
it's like it's giving credence to that message. I understand that there's no verifiability, but I was trying to think of this as if it relates more to what happens with like die evidence or now there's a message that I understand that there's other messages that but this might be too far field.
Yeah, let's talk about it later. I'm not quite sure. I will emphasize, so with the Brownian motion, we get perfectly aligned interests here. This result is not special to the Brownian motion, right? And it can work with many different classes of functions here. What we really need is this what we call response uncertainty. But we need the receiver to not be sure about what's going to happen when he responds, if he overrides the recommendation. And so, in fact, we can do this with the beauty of the Brownian motion is we can do that with continuous functions. So when it's a continuous function, it has to go up for that to arise. We provide examples in the paper where the function can be discontinuous and it jumps down. All right, and the same sort of logic happens. I'm worried that if I move to the right, there's a chance I'll jump way down and pass my ideal point. And it doesn't have to be that interests are perfectly aligned as well. We'll give examples where the expert can send a message such that their interests are never aligned, but the receiver's response uncertainty is so great that he's bound to accept that recommendation. I can talk about that more at lunch. All right, so the Brownian motion, I think, is a very elegant way of capturing this, and it does it with a continuous function. Right? But the logic is not dependent upon it. All right, I'm going to run out of time, so I want to not do that. And just sort of wrap up talking about this model and this approach. All right, so I made the point at the beginning that I think this richer information structure is relevant to many domains in economics. So I've worked on experimentation and search, and John has 2 beautiful papers so far that I know of in this domain. I'm now talking about strategic communication, which I think is another important domain. And what I think sort of comes out to me when I talk about it this way is that there's interesting dynamics and interaction between these 2 areas. So if I don't listen to an expert, I have to experiment. Right? And so in many respects, my choice about experimentation and experts are the one and the same. I either listen to an expert or I experiment. Right? And I think there's a lot of, it's going to be perhaps difficult, but opportunity for interaction across that. Another area I wrote one paper on, and Ariad is the master of these days, is what we call the attributes problem. So where you care about the whole function rather than just trying to find one good action. Suppose I cared about the whole function to determine whether a policy is good or bad. And what I've been working on as well lately is integrating this logic into a model of industrial organization, of firms competing against each other. So this experimentation can also be thought of as a model of innovation, firms searching for good products or technological breakthroughs. And they have to do that while they're competing with other firms. All right, so that's another application I have. Been thinking about this. There's probably many more. If you have any ideas or questions or thought, feel free to email me. And there's my website. And I have a bit of a write-up there. On that page, you'll see a link to a bit of a write-up of these different domains or applications that I've worked on and other people are working on if you want to get up to speed. Good. Let me stop.
So you painted this very clear picture of, with one parameter, the decision maker has all the power. With continuum many parameters, expert has all the power. This prompts the question: what about in the middle? If you have, like, do you have any idea of function classes?
No.
Okay.
So I can do my expert has all the power for different classes of functions. We're at the moment categorizing them into a typology of the different things you need. What I have no idea about still is what are equilibria between those two cases, where the Crawford-Sobel, the receiver, has all the power, and my equilibrium where the expert has all the power. What makes my case easier is I don't have to worry about the incentive compatibility constraint for the expert because she just gets what she wants. And so that's the easy thing. If I'm somewhere in between, I could conjecture to you for a couple of hours, but I really don't know what that looks like. I mean, my holy grail in this is some beautiful continuum of equilibria that goes from this one to Crawford-Sobel at the other. And we're not there.
Yeah, sorry, this is a very naive question. I don't know a ton about these Crawford-Sobel models, but like, if I was going to take a learning perspective on this, so I could think of this as like a repeated game, and there's a learning perspective. From that perspective, you don't like you could write down what the equilibrium is, right? Like I know what the equilibrium is if I know the utility functions, but I don't necessarily need to characterize it to learn it, right?
Characterize what? The equilibrium?
Characterize the equilibrium to learn the equilibrium. You can write it down, you just may not be able to compute it. Or is that like, so like, I guess my question is like, has anybody thought about that? So A, is my question reasonable? Like, am I saying a true statement? And again, very new to this. B, is it a perspective that people take where it's like, you know, there's some equilibrium out there. I don't know what it is, but what I'd really like to do is play a game. And that's where the learning comes in. I'm just saying this as a bandit person. I don't need to know what your equilibrium is to try to find it. It could help me to know what it is to find it, but I could still try to learn it.
Lots of interesting things there, but I don't quite know what answer to give you. Learning equilibria is a whole separate field in economic theory. Right? Two players, perhaps a coordination game, we're going to play and we're going to try to learn that equilibrium. That's a whole separate equilibrium, that whole separate area. If we did this dynamically, I think that's another feature that stood out to me about Crawford-Sobel. If we did that dynamically, it would be boring because in the first period, like if you didn't listen to me, you would just choose a point. Then as soon as you chose a point, you would know the whole function if you saw the outcome without noise.
But in your model, that's not true.
In my model, that's not true. And so I think that's another thought I've had. My model opens up some interesting dynamics, and it opens up this interesting combination of experimentation and cheap talk. Like, so maybe in the first period, the structure is such that we can't communicate, so you have to choose a point on your own. But once you learn a point, then we're in a world where we can communicate. And I can give you examples where that happens, but I just haven't solve anything.
Thank you.
Got a time, Laura? One more quick one.
I'm a little confused about physics experts. The expert knows all the information, even including the future. I mean,
There's no future.
he don't know about the future.
No future. So one-shot model. And so this often it gets confusing when I talk to people. The more people know about the Brownian motion, the more confused they get because they always think of it as time. There's no time here. The Brownian motion evolves through the action space. And so you're just choosing actions that produce outcomes. It's just like there's some function there.
So
Instead of a quadratic or a linear, I'm just saying nature drew a Brownian path. Pick the status quo, draw one in both directions, and that's my world.
so there's no T, but just action on the X.
Action, yeah, exactly. It's the same in John's model. The path is there, you're learning, he's got time, but you're learning this path over time. But in a sense, the path is already there. And that's the sort of key trick or approach is to use it without time as the independent variable, but have some action space. All right, much time. Thank you, everyone.